don't want to. Okay, so the idea here is we want to prove some trig identities. So if I have something like secant theta sine theta over tan theta plus cotangent theta equals sine squared theta. Okay? So the idea is we have some we have an equation here that we don't know whether it's true or not. Right? So we're trying to prove that it's true. So as I said yesterday, I really want to emphasize this because this is the biggest temptation to do things wrong, is you cannot treat this like an equation, meaning that in an equation, you can add the same thing to both sides of the equation, or you can multiply the same thing to both sides of the equation, and essentially what it enables to do is to move things around, right? And so we can't do that because you can only do that if you have an equation that you know is true, right? This thing, I don't know if it's true or not. We're trying to prove that it's true. So you can't assume something that you're trying to prove, if that makes sense. Okay? So really the only thing I can do here is work on one side or work on the other side and try to get them to look the same. So, what can I do? Well, one thing you can do, and this is pretty much always the first thing I do, is I can change everything to sine or cosine. Okay? Often that is a nice maneuver because you see some sines on top and sines on the bottom that can cancel out, or you see a sine squared and you can turn it into a cosine squared or something like that. So that often produces some nice things that kind of present themselves, right? And an even better option, if you can, is to change everything to the same trig function. Meaning if I can change everything to tangent, that's going to be even nicer, isn't it? Because then absolutely everything will be able to cancel or combine together, something like that. If I'm working with only tangent, then it's a lot easier to work with. If I'm working with tangent, secant, cosine, and cotangent, then there's just a bunch of stuff that I won't be able to see whether they cancel or not. Okay? So even though I put them in different orders, I put the one as number one because that's the one you use most often. But really, if you can do number two, that's better. Right? If I can change everything to one function, one trig function, then that's going to work nicely. If I can't, then I'll change everything to sine or cosine. Yeah?
So in that kind of situation, would you want us to, like, if you had sine squared to change, and you were going for all cosine, would you change it to 1 minus cosine squared?
Right. So when I say change everything to sine or cosine, it means obviously the numbers are still going to be in there and stuff like that. Yeah. But you just don't want any trig. You only want one type of trig thing in there. Yeah. Okay, that was a nice clarification. Thank you. Okay, so going on to number 3. So those are the major trig. Oh, let's back up a second. How do we do this stuff? Well, of course, we're using all the trig identities that we know. What are the trig identities? Well, they're like tangent of theta equals sine over cosine. Right? Of course, these are things you already know, right? Secant of theta is equal to 1 over cosine. Cosecant, I'm not going to write all of them because you know all those, right? So all these trig identities that we've already known and we've been using for quite a bit, those are all things that enable me to change from one trig function to another, right? And the other ones are the Pythagorean identities, which are sine squared theta plus cosine squared theta equals 1. That one's nice. And we got secant squared theta is equal to, and I always forget this one. Is that tangent squared plus 1? Yeah. So that'd be tangent squared theta plus 1. And then the other one is, cosecant squared theta, and that's equal to cotangent squared plus 1. Right? So these are the Pythagorean identities. They're very useful to change things from one trig function to the other. And then there's, again, these are not all of them up here. But there's more of those, but you know all those, right? Okay, so that's what when I say in number 1 and 2, that's what we're going to use in number 1 and 2. We're going to just sub out things that are equal. So if I have a tangent in my expression, I can change it to sine over cosine. Right? Okay. Step 3 is algebra. What kind of algebra? Well, I can find a common denominator. And add fractions. Right? That's a move we did a couple times yesterday. Find a common denominator and add fractions. Everyone know what I'm talking about? Right? What else can we do? We can divide fractions by flipping over and multiplying. Right? So if I have 1 over sine divided by sine over cosine, I can flip the sine over cosine over and multiply, and hopefully some things will cancel out, right? Or at least they'll combine together. So I can divide fractions. And this one's less often used, but I can do it. I can separate fractions. Oops. What on earth do I mean by that? For example, if I have sine x plus cosine x over cosine x, I could rewrite that as sine x over cosine x plus cosine x over cosine x, couldn't I? That's what I mean by separating fractions. Sometimes that's a decent move because if I have one term on the left side but I have 2 terms on the right side, it's good to separate that out because maybe adding the 2 together would be a problem. Okay, so that's what I mean by separating fractions. That only is doable if I have just like one term on the bottom, right? What else could I do? I could also cancel, but make sure you don't do any bad canceling. Right? In other words, if I have sine of x times cosine of x over cosine of x, that's a case of where I can cancel, right? Because cosine is a factor of top and bottom. I can cancel the cosines, and I'm left with just a sine x. Yes? But what if I have sine x plus cosine x over cosine x? Well, there's nothing that can be canceled there. Because cosine is a factor to the bottom, but cosine is not a factor to the top. Right? So I cannot cancel the cosines there. That's a temptation for a lot of people because they never learned how to cancel properly. Yeah.
You can separate that into like sine x over cosine x plus.
Right. You could, like we did up above, we could separate it into 2 fractions for sure. Just that what scares me is people go like that and just say, oh, it's just sine. That's bad canceling, right? Or even if you said, oh, it's sine plus 1. Again, that's bad canceling. Nope, that's not the way it works. Right? But yes, the proper way to handle this would be to say, like we did above, I could break this into 2 fractions. That'd be sine x over cosine x plus cosine x over cosine x. Now, in this fraction, cosine is a factor of the top and the bottom, isn't it? So that is 1. And I'm left with really tangent x plus 1, aren't I? Not sine x plus 1 or some other weird thing. Okay? All right. So that's the main moves. Canceling, I guess I should say there. Did I spell that right? Cancel. Yeah, I think so. So that's canceling. That's the main algebra moves. And again, why I threw them all into one, because usually what happens is we do one of the first 2 moves, and then we look at what presents itself. If there's 2 fractions that have a common denominator, it makes sense to just add them together. That would be helpful. Or if we have 2 fractions that don't have a common denominator, but the other side is just one term, it makes sense to get a common denominator and add them together, right? So you just look at what presents itself, and you make one of these algebra moves. Okay? There's some more obscure algebra moves that we might use occasionally, but these are the main ones that you use all the time. Okay? All right, so let's scroll back over here. And just to be abundant, I think I did this one in class yesterday, but I'm going to do it again. And I'm going to do it a different way. Maybe. Yeah. So I notice here that secant is 1 over cosine, right? Well, I'll just do it. This is 1 over cosine theta times sine of theta. And down here, this is tangent of theta. And cotangent is 1 over tangent of theta. So when I did this yesterday in class, we changed everything to sine and cosine. You remember that? But now I'm going to try to do the number 2 option. Because you notice when I write that top is just sine over cosine, isn't it? Isn't it? Sine times 1 over cosine, that's sine over cosine. And sine over cosine is tangent. So I could rewrite this as tangent theta over tangent theta plus 1 over tangent theta. And now we've achieved the coup d'etat. We've got everything into one function. On the left side. I remember at this point I forgot about the right side. I don't really care about it right now. But this side is nothing but tangent. Oh, that's a rare find, yeah? No, it doesn't look any prettier really, but at least it's all tangent. So now we look at, this is where the algebra comes in. Is there something we can do here? Any ideas? Yeah.
I think we can do something because we can cancel the tangent out.
Absolutely cannot, because that's an example. Thank you for saying. I told Robbie to say that. He doesn't really think this. That would be a case of bad canceling, wouldn't it? Because tangent theta divided by tangent theta is 1, but in this case, tangent theta isn't a factor of the bottom, right? Right? Okay, but what I can do is I'll call this tangent theta. And then on the bottom here, I'm going to change this to tangent squared. Or, no, I'm not. Yes, I am. I'm going to change this to tangent squared theta over tangent theta. Why did I do that? Because I want a common denominator down here. Right? So I'm going to add those two bottom pieces together. So I need a common denominator. So then when I do that, I get tangent of theta on top and tangent squared theta plus 1 over tangent theta. Yeah? And now I have a fraction divided by a fraction, so I could just multiply by the bottom, the reciprocal of the bottom, right? And so then I am going to have tangent, and I'm doing this carefully one step at a time so you can see it. Tangent squared theta plus 1 times 1 over tangent theta. Yeah? Notice I've long since forgotten what that other side looked like. But what happens when I do that? Now the tangents can cancel, right? Because tangent is a factor of the top, tangent is a factor of the bottom. So these things will whoop, whoop. And I'm left with 1 over tangent squared theta plus 1, which is not that exciting, except for, is there some trig identity that can help me out here? That is secant squared, isn't it? Yeah. So this would be 1 over secant squared theta. Oops. Yeah? Now we can go back and see what happened on the other side. What's happening over there? Sine squared. Uh-oh.
You have a question.
Yeah. Help me out. I did something wrong. Say it one more time.
So instead of times 1 over tangent theta, it's actually times tangent theta over tangent square theta plus 1. Because that's whole estimate.
Oh, I missed up which was on the bottom, which was on the top, didn't I? Ah, yeah. All right, let's go back up and fix that. Everyone see what she said? See right here, I was thinking the bottom was this guy, but really the bottom is this whole guy here. Let me use my highlighter so I'm not helping you by saying what I just said. Ah! What I'm really meant to say was, highlight. This is the bottom fraction, isn't it? I was thinking that tangent was the bottom fraction. I lost track of the bottom. Okay? So down here, I'm going to have change that. Okay. So really what I should have had was tangent. It didn't stick. There we go. What I should have had was tangent of theta times tangent of theta. Oh, that'll be nicer now. Over tangent squared theta plus 1. Yeah? So then I have tangent squared theta over, and tangent squared plus theta plus 1 is secant squared theta, right? Now we're trying to get sine squared theta, right? Yeah, okay. So let's see. Does that give me what I want? Yeah, that's going to be sine squared over cosine squared. And that's 1 over cosine squared. So if I better do that. So that's 1 over cosine squared. Yeah? So now when I multiply by the reciprocal, I get a cosine squared on top. And those cancel out. I'm left with the sine squared theta. There it is. Yay. And there's much rejoicing. Yay. Okay? So I'm kind of glad that I made that mistake in front of you. I'm not going to all claim that I did it on purpose. That would be dishonest. But because you see that this sort of thing happens sometimes, and you have to back up and try to figure out where you went wrong. And it's helpful if you have a watchful eye over here kind of checking on you. But if you don't, you have to kind of go back and be your own policer and say, I didn't get them to match up, so I got to go back up my steps and find out where did I make the mistake. Because if you're doing each step logically, you should be able to go backwards and figure out, okay, was that step really right? Yeah. Was that step really right? Oh, shoot, I did a bad canceling there. Okay, and then fix it. Or, like I did, I divided by the wrong bottom. Okay? So that's the nice thing about these, why it's also especially important. Besides, you won't get full credit if you don't do this, but it's why it's also especially important to really do it seriously step by step. Don't skip steps, because that way you can go back and follow your own logic, right? And you can possibly find a mistake. Because I guarantee you're going to make mistakes on these. I mean, I've been doing this for 30 years, and I just made a mistake.